Hi, my name is Manish Gupta, and in this video, I'm going to talk about an interesting topic of scaling data-constrained large language models. Okay, so this is a paper, this is based on a paper that was presented and won the outstanding main track runner-up at NeurIPS 2023. So let's talk about these scaling laws, so to say. So some of you might have heard about the Chinchilla scaling law, which was made popular in the Chinchilla paper. And then there is this another scaling law that I'm going to talk about, which is proposed in this paper called as data constraint scaling law. And I'll also talk about why they are required and so on. Okay. Now, when you look at large language models, of course, people have been trying to build larger and larger and larger models. But then when you're trying to build these larger models, there are a few things that you can change. Either you could basically increase the number of model parameters, or you could increase the amount of data that they are trained on. Whether you increase the number of parameters or you increase the amount of data that is being used to train, in both cases, you end up actually increasing the overall compute that is required to train these models. So now the question is as follows: if you have a fixed amount of compute that you know, right? Now, and you have to and you have to decide that, hey, how many parameters should I have in my model versus how many tokens should I train it for? How do you select between those two? How do you select between those two? Okay. To be able to make that decision, what you need is some predictive scaling law of large language models to decide what kind of training resources should be used, right? So the two questions are: what is the optimal balance of resources? And as I said, the resources could be in terms of pre-processing, in terms of pre-training data, or it could be in terms of, increase in model parameters. Okay. And if I'm using X compute, if I basically use 2X compute, what is the ROI? What is the, what is the expected value of those additional resources that I put in? Okay. So broadly, resources can be considered as or other compute. I'm just using the word compute or resources interchangeably. You could express it in terms of floating operations per second. So floating point operations per second, also called as flops popularly. Okay. And traditionally, flops has been estimated using this simple formula for large language model, 6ND, where N is the number of model parameters in the large language model and D is the tokens processed. Okay. So the optimization problem, so to say, is basically this one. You have to minimize the loss. So you have to train a model and you have to minimize the loss via optimal allocation to N and D. So you have to basically choose your model's number of parameters and the number of tokens that it must process. Number of tokens is basically a proxy for the pre-training data that you're using, right? So you must choose the right N and D so as to minimize the loss. Okay. So you could express it this way that, hey, I have to minimize this loss, based on the N and D, the number of parameters in my model, and the tokens processed, such that my overall compute is limited. So flops basically is C. Okay. And in the Chinchilla paper, essentially they came up with this form of the loss of n comma d, because the idea is that yes, if you have larger number of parameters, your loss should be smaller. And similarly, if you're training on larger amount of data, your loss should be smaller. Of course, so therefore it justifies why n and d are in the denominator. Now in this formula, if you look at it, A, B, E, alpha, and beta are all hyperparameters to be tuned on a particular data or a language or a family of models, right? Um, and they did all the math and they figured out basically that the optimal values of n and d can be given as follows, where there is a factor called g, which is basically like that, right? And I'll not get to the math, but they have some formula basically based on which they could solve this and figure out, these values. What they came up with, though, is that alpha equal to beta basically is a good solution. So, whatever the values of A, B, E. So, of course, all of those values are dependent on the family of the model and also on the kind of pre-trained data that you're using and so on. It varies, right? But the point is that they basically said that whatever you do, alpha should be almost equal to beta. Okay. So as to have optimal allocation and optimal return ROI from your additional resources that you're putting in to train these large language models. Okay, which basically meant that N and D should be scaled proportionally for compute optimal training, which basically meant that, hey, if you're scaling your pre-trained data 2 times or you're just increasing the model size in terms of number of parameters 2x, you would get similar kind of effect in terms of the loss that you can obtain at the end of the training. Okay, so a nice decent story, but this story basically made sense uh, when you had pre-training data that was consumed for only one epoch, in the sense that you would not look at the data again. So there was no repetition in the pre-training data, right? Which basically meant that to be able to train models which are highly accurate, where the loss is super low, you would want to basically get pre-training data which is crazy large, maybe as large as the internet, right? And we are reaching that limit. I mean, there is only limited amount of training data. And if you think about multilingual models, training a model on Hindi, clearly you do not have lots of training data available, right? So therefore, what you need to do is to repeat that data. You need to do several epochs over the same pre-training data. Okay. Under those several epochs, essentially, let's say if you have limited unique data, and let's call it DC, under that kind of a situation, how do the scaling laws look like? Now, that is what is called as data constraint scaling law, and which is what is proposed in this paper. So what is the data constraint scaling law? It is basically a law which sort of indicates how you should allocate your resources to number of parameters in the model or number of tokens to be processed when you do not have enough pre-training data, and you must do multiple repetitions, RD number of iterations over your unique tokens UD. Okay. So if you have unique amount of data, you must do repetitions over it. And then in those kinds of cases, how does the scaling work? Okay. So your optimization now becomes this, that you have to basically minimize the loss. Of course, you always want to minimize the loss, right? You want to get a good model such that the compute is limited, but also the pre-training data is limited. The number of unique tokens are capped by the overall available unique data for that particular setting, okay, for that particular language, for that particular domain, and so on. Okay. So now to be able to solve this problem, again, you have to basically do some math. So you have to basically express it as an optimization and so on. So they said that, yes, we will do the same thing. We'll essentially, use the same form. It's just that rather than using n and d, we'll basically use n dash and d dash. Now, what is d dash? Well, d dash basically is a combination of the unique data that exists UD plus, how much importance should I give to repetitions on data, right? So remember, when you're doing one epoch over data, every data point is new, and therefore the model has something to learn from. But the hypothesis in this paper is that as you see more and more data, as you see the same data several times, the more number of times you see, the worse its importance or the worse its impact gets on the training of the model, right? So in fact, they basically come up with the exponential decaying impact, where they basically say that, hey, if I look at it like twice, then maybe the impact becomes half. If I look at thrice, the impact becomes 1/3, and so on and so forth, right? So therefore, these d dash and n dash are basically just a representation. So specifically, d dash is basically just saying that, hey, if I look at the unique data, that's UD, and it has its value, that's great. But the remaining part of the data, the remaining repetitions, RD repetitions that I do of the data, have a declining value rather than the original value, declining value, exponentially declining value. Right. So that's that. And now for mathematical nicety, right, they actually split n dash also into two parts: the base parameters UN, which are optimally required to fit this data UD, and then there are other parameters, which have marginally improving ROI on top of the original set of base parameters UN. Okay. Again, this kind of a split of those parameters are actually done for mathematical ease, so that they can solve and get a good solution to this kind of formulation. Okay. So remember here, the solution was simple. You basically do alpha equal to beta. But in this data constraint scaling laws, it turns out that alpha equal to beta is not a good solution. In fact, there is a better solution, which I'll talk about on the next slide. Okay. So to be able to do these experiments and figure out these things empirically, they actually did experiments on resource allocation for GPT-2 trained models. So GPT-2 trained models on subsets of C4. So they are using data from the C4 large data set, right? And they're training GPT-2 kind of models. And they trained several such models. So basically, they made sure that they are using 100 million parameter model. So in this particular case, they kept the number of 100, sorry, they're using 100 million unique tokens. So they're using a subset of C4, which is 100 million unique tokens, okay? 100 million unique tokens. And they varied the number of parameters, and they also varied the number of epochs or for which you will basically run this model. So the 100 million unique tokens, of course, if you run like 1,000 epochs, you're basically talking about an overall 100 billion compute, right? 100 billion pre-training tokens in that sense is overall non-unique ones. Okay. And they trained several models. So as you see, these dots basically indicate the models that have been trained. So they trained 93 different models with varying number of parameters and varying number of epochs. Okay. So, and then they basically get some loss values, which are essentially what are plotted here. In fact, the contours here essentially are estimated densities. So basically what you see is that the loss contour, the loss basically, of course, if you look at one epoch model kind of loss, basically, based on the chinchilla laws, they essentially found that for 100 million tokens, one epoch compute optimal model is essentially 7 million parameter model. Okay, so that's what the chinchilla laws say. And this dotted line basically is the chinchilla line. It basically says that if you want to increase the number of tokens or you want to increase the parameters, both of them can be varied in an equal way in that sense. So alpha equal to beta approximately, and that's the chinchilla law. Okay. Um, but what you see from the actual practical loss values that are computed, first thing to observe is that if you increase the compute, from one epoch to several epochs, several repetitions on the same data, you don't need fresh data always, right? Several repetitions on the same data, you basically observe that the loss drops significantly, right? So essentially, in fact, there is 50% plus reduction in loss that can be obtained by training for several epochs and also by increasing the model size. So if you increase the model size, basically the loss drops significantly. Okay, that's one observation. Okay. The second observation, and then they observed that the best loss is actually obtained when you're using 20 to 60x more parameters and epochs. Okay, so in fact, that's that. And the other observation also is that if you basically increase the number of epochs or the number of parameters more, you do get into regimes where the loss actually starts increasing in the sense that you of course want as low loss as possible, but if you basically are not very careful and you just increase too many epochs, it starts overfitting or and essentially you lose the nicety that you obtained by just increasing in a careful manner, increasing the number of parameters and number of epochs. Okay. Now, if you basically went ahead with the optimization solution that was proposed in the previous slide, the data constraint scaling law, and a solution to this theoretical framework, you basically obtain curves of that kind. Okay, the curves that you see here, which very much match with the curves that you see here, right, in the actual. So the left one is empirical, the right one is basically what is observed. Okay. Now, of course, you see the chinchilla law there, but what you also observe is that based on these curves, you can actually draw an optimal scaling kind of efficient frontier. And what you observe is that this one deviates from the chinchilla law. So chinchilla law basically says approximately alpha is equal to beta. So you don't care n and d. You want to scale you reduce the loss. You could scale your model or you could scale your pre-training data. Both of them have similar effect. Okay. Um, but what is observed is that when you're repeating the data, basically that law does not work. It deviates. In fact, what is observed is that excess parameters decay faster in value than repeated data. And therefore, in a data constrained situation, your efficient frontier suggests that allocating more additional compute to more epochs rather than more parameters. So basically, if you want to do if you essentially want to train better models with the same compute, you would rather learn smaller models, but with more number of epochs, smaller models, but with more number of epochs. And they experimentally validated it by actually, finding that real model, that empirically validated that the lowest loss model actually follows the data constraint law rather than the chinchilla law. Right? So that was about allocation. So essentially you have resources and you want to allocate. What is the best way to allocate, whether to parameters or to models or to basically pre-trained data? And they observed that it is better to allocate more compute to doing more epochs, more pre-trained data, more epochs, more repetitions on the existing pre-trained data rather than actually training larger models, which is, by the way, nice because that just means that you can actually have trained smaller models. In fact, they basically also showed that a 120 billion Galactica model trained on the repeated data could have been 3x smaller in size compared to the original Galactica model with the same flops, right? Now the other question is about resource, right? So essentially, yeah, I mean, if I have a limited amount of pre-trained data, sure, I can do more repetitions and I can train larger models also, but I can repeat over several epochs and train for longer time, longer duration, right? Which basically means I can put in more and more compute. So how much more compute should I put in, right? Is it worth it? Is the question, right? So what is the ROI, right? And that's the answer that we see on the slide here. So basically for the left plot, so I'll first talk about the plot on the left side of this one. So basically they experimented with three different size of models, 2.8 billion parameter, 4.2 billion parameter, and 8.7 billion parameter models. they assume that they have pre-training data of that sizes, 55 billion tokens, 84 billion tokens, 178 billion tokens. And they actually, so this was the overall data that they had, but they basically did several epochs. So the idea was that they would essentially, if you look at the 55 billion thing, you just do one epoch. But if you basically just use 28 billion tokens, you repeat it 2 times. So that's 2 epochs. Similarly, if you want to do 3 epochs out of the same data, you just sample like 18 billion tokens, and then you see it 3 times. So effectively, you're looking at 55 billion tokens, but in the first case, you're just looking at it once. And then, second case, you're looking at the same token twice. Third case, you look at same token thrice, and so on. Okay. So now it's sort of obvious that if you basically look at, if you just do one epoch, then you should get better results, lower loss, right? But if you do 2 epochs, you will get, slightly worse loss, 3 epochs, slightly worse loss, and so on, or rather slightly higher loss, right? So that is what is plotted here. So you see, this is 2.8 billion parameter, 4.2 billion parameter, 8.7 billion parameter models. And, one epoch basically means 55 billion tokens here, 84 billion tokens there, and 178 billion tokens there. So, and what you see several curves in every subplot, right? So what you see here is that if you actually do 44 epochs, basically you're using 1/44th of that data, just 1.2 billion parameter of, 1.2 billion tokens from the data, you really get very bad loss, very high loss, right? But if we are doing, of course, just one epoch, basically, just one epoch, every time you just see a fresh token, right? You basically get like a very good model, very low loss. Okay. But what is important to observe is that if you do 1 epoch, 2 epochs, 3 epochs, 4 epochs, you essentially do not see much of a difference. Basically saying that even if you use repeated data, rather than actually leveraging the entire 55 billion parameter data, you still can improve on the overall loss. And that's a very important observation, because for languages, for data constrained and data, low resource languages, you do not have enough labeled data. And therefore, what this law suggests is that if you basically, repeat the data 4 times, 4 times, 10 times, maybe, even if you repeat up to like 10 times, it is as good as having, 10x sized original data, unique data. Okay, so that's an important observation. Okay. The second thing is observed on the right side. So on the right side, what do you see? So you see on the x-axis fraction of training tokens that are unique, and on the y-axis, you see test loss. Okay. And you basically see 3 curves for 3 different model sizes, right? So that's that. Now, of course, this one basically corresponds to 100% fraction of training tokens, which basically means that this is your best model for different parameter ranges. Okay. Now, if you basically use 50% data, this basically means that you're using the 50% of the data, 50% of, let's say, your 55 billion parameters, and then you're trying to train your model by doing 2 epochs over it, right? So what you observe is that, of course, your model gets slightly worse, but not noticeably worse. In fact, what people observed is that, even if you do it like 4 epochs, you don't really get a very worse model. You get like almost similar kinds of models, almost similar kind of a model. Okay. And in fact, what you also observe, so these dots are actual values as observed by training models, and those curves are actually the ones that are trained that are obtained using the data constraint scaling law that I talked about on this one using this mathematical formulation. Okay. So those dots are very close to lines, which basically says that the data constraint scaling laws are actually accurate, are actually reasonably accurate, specifically as against chinchilla laws, which were never meant for data constraint kind of scenarios where you repeat that pre-training data. Okay. Now, this last plot is actually super interesting. What does it say? So on the x-axis, you have total training tokens. On the y-axis, actually, you have final test loss, right? So the lower the loss, the better, of course. And you have 3 curves basically for 2.8 billion parameters, 4.2 billion parameters, 8.7 billion parameters, right? Of course, you could do 1 epochs, or you could basically do several epochs on the overall data. So 55 billion tokens, 2.8 billion parameters, I do 1 epoch, I get this kind of loss. If I do two epochs on top of it, I get that kind of loss, much lower, which is good, because if I repeat the data, it's not that I don't decrease the loss, I decrease the loss. So it's better to repeat and do more epochs. Okay. If I do 4 epochs, I basically decrease the loss further. I do 8, I decrease further, 16, I decrease further. But beyond that, the ROI is not much. So this curve basically talks about ROI, right? What is the resource return when I invest more resources? Okay. If you do up to 16 resources, that's more than enough. 16 epochs, that's more than enough. Never do more than 16 epochs is the takeaway from this paper, right? It's basically saying that, especially in these parameter ranges, 2.8 billion parameter models, doing more than 16 epochs basically does not really lead to any good ROI, Okay, so that's the good takeaway. Okay. So in summary, in this paper, basically people came up with an extension to the chinchilla scaling laws that considers decay in the value of repeated data, right? If you repeat the data because of data constraint settings, what does the law look like? Okay. And they also basically talked about training LLMs for multiple epochs by repeating data and found that repetition of data is beneficial. Okay. So, this chart basically just shows the same thing. It basically says that, yes, if you are x-axis is number of tokens or epochs, y-axis is final test loss. And what it says is that repeating data is beneficial, especially if you're repeating up to, let's say, 4 times. So if you basically do 4 epochs, it's great because it's almost as good. So the dotted curve is basically what happens if you had, if you assume that repeated data is as good as new data, right? That's more like chinchilla law, right? Chinchilla scaling law. But then you see it is not always as good. So up to 4 epochs, it is almost as good as new data. But beyond that, of course, there's deviation from new data, right? And that's basically the law that is proposed in this paper. These dots are actual observed values. The curve is, of course, drawn as per the law. Okay. And what you observe, therefore, is that the real data constraint frontier is not x equal to y line or alpha equal to beta line when you compare increasing number of parameters of a model versus increasing the amount of pre-trained data. But it is more of this line, which basically prefers prefers training smaller models with increased number of epochs, smaller models with increased number of epochs. Okay. So that's it for this video. Hope you liked it. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.